Wonderful. I hope you can all see the slides, and I just want to extend my welcome and to really just thank you for joining us and giving up 1 hour of your time this evening. You're obviously here, I hope, because you want to find out more about computer science at Cambridge. But I thought I would just start by introducing myself and the college a little bit. So my name is Luana Bulat, and I'm a Director of Studies in Computer Science here at Mary Edwards College. Now, as a Director of Studies at Cambridge, I look after all the computer science students at Mary Edwards and oversee their academic progress and development. We are incredibly proud to host the largest cohort of female undergraduate computer science students within the university. That's really, really big for us. And really, it is my mission and my job to support our students in their degree and ensure that really they will achieve their potential. I'm also a college lecturer in computer science, also here at Mary Edwards College, where in that capacity, I teach a wide range of subjects from the undergraduate computer science tripos, ranging from mathematics to machine learning. And a third hat I have is that of an admissions interviewer for computer science. I have taken part in over 600 interviews to date. I've been part of Mary Edwards for almost 5 years, and it really is a place where both my students and I feel incredibly well supported to become the best version of ourselves. So just echoing Emma's message from before, I just really want to encourage you to visit us during the open days. I think they're on the 4th and 5th of July. But Mary Edwards is really a place that you need to experience firsthand rather than just read or hear about it from me or anyone else. So when I'm not teaching, I work on my research, and very broadly, this focuses on teaching computers to understand the meaning of natural language through text and images. This falls under the umbrella of natural language processing, which is a branch of artificial intelligence, language understanding, and multimodal learning. But enough about me. Just to lay out the plan for tonight, I thought I would actually start by talking a little bit about the computer science degree here at Cambridge. And because invariably there will be questions about the admissions process, I will briefly touch up on this. We will spend the remainder of our time together then delving into a mini lecture on finite state machines to just give you a taste of what it's like to be an undergraduate student doing computer science. And since computer science is best learned by doing, I will also ask you to think through some exercises throughout the lecture. So please find some pen and paper or anything really that you can write on if you have a tablet, just in order to get the most out of the session. Now, don't fear, I'm not going to put you on the spot because this is a webinar, so you're safe from that. But it will really help if you think through the problems and see if you would like to do a degree in computer science. Starting just with a very, very brief description of the department here at Cambridge. The department has a long history. It's 80 years old, which in computer science is a very, very, very long time. And is known really for some early developments in systems research, in particular, like the first stored program computer. Now, today, the department continues to be a center of excellence in computing research, and it is really very open and collaborative in nature and culture. I've listed on the slide all of the current research areas, and just to allow you to process them, I'll just name a few. Everything from bioinformatics, computer architecture, computer vision, natural language processing, machine learning, logic, systems, programming, security, anything and everything, really. And I think one of the big selling points of Cambridge is its really, really strong ties with the industry in the surrounding area. You might have heard about the Silicon Fen. Now, when we think about computer science, we might think about today's fancy technology that we interact with on a daily basis. But doing a computer science degree at Cambridge is more than that. It's about learning the principles that will outlast today's technology. So in your first year, you would have courses on foundations of computer science, maths of different types. You would learn some programming and electronics. You then move on to your second year, where you will be taught the core ideas in systems and theory, and you will also do a group project. And then in your third year is really where you specialize. So you actually have a choice of various specialist courses that you might want to do and an individual project, which we then culminates with a dissertation. It is increasingly popular for people to stay on for a fourth year and do an integrated master's degree. And our graduates are in demand across both industry and academia. Now, I did warn you, I'm going to mention briefly what happens during an admissions interview, in case you were wondering. So a possible setup for 2024, interviews could be held in person or remotely. It would depend on the college. So I would encourage you to consult the university's admissions web pages. But for Murray Edwards, they would be online. And it would be you and two interviewers. There's kind of a snapshot of a Zoom call that we were on, where it would be roughly about 30 to 45 minutes in length, and you would be asked a series of maths and logic questions. And I've put it up there on the slide that really no equipment is needed other than a device with a stable internet connection. So pen and paper would work to show your workings. You can just use a thick pen and your paper to show what you've written to the interviewers. So you don't need anything fancy. And probably the single most asked questions I get about admissions is, what are you looking for in a candidate? My take on that is we really look for natural aptitude for computer science. So what's special about Cambridge is that, well, we don't require necessarily you to have a programming experience, because we believe that throughout your studies, we will provide you with all the knowledge you need in order to be a successful computer scientist. So during the interview, we really want to find out whether the candidate has a natural aptitude for computer science, which really means we just want to see how you think. Most often, we would just use real-world examples to model computer science problems, like water flowing through a pipe, to model networks, network packets flowing through the internet. So we don't assume or assume very little computer science knowledge. And really, the interview is a conversation. We're not trying to catch you out. We're really, really just trying to stretch you and see how you think and how far you can go in the question. All right, so now that you know what I do, how wonderful Murray Edwards is, and you have a little bit of background on the computer science degree at Cambridge, we will just dive into today's lecture. So I thought I would talk about finite state machines, and in the spirit of the computer science degree here at Cambridge, which is slightly more theoretical in nature, today's topic falls under what we call the theory of computation. As I said, we will specifically focus on finite state machines or finite automata. They mean the same thing. Now, our goal is to really understand what computers can do. That is, what can we compute using a machine? However, today's computers are very complex objects. It's very difficult to describe and manipulate them mathematically. So we will just use some abstract models of computers. They are much simpler, of course, but they effectively capture some very important properties that we are trying to understand and reason about. So let's just take the TV remote, for instance. And if you think about the power button, we take it for granted that pressing that power button will turn the TV off if the TV was on, or on if the TV was off. But we're pressing the same button. So what really is that is telling the TV to behave differently? Well, it's the state of the TV. We can represent this very easily through what we call a finite state machine. That would just have two states. The TV is on or it is off. And the action we apply, pressing the power button, just changes the state of the TV. So depending on the current state and the action, we would know what to do. Now, we can use these finite state machines to represent vending machines, elevators, traffic lights, video game characters, and a lot more. So this machine that we're going to look at today, as I said, is a very simple computer with a very small amount of memory. But again, the nice thing about them is that they're so simple that we can really understand them very well, and we can reason about their properties, as I hope you will be able to do by the end of this talk. All right, so here is a finite state machine as a state diagram. That's what we refer to is the diagram you see there. And you will just see circles and lines and some labels on them. So the circles are called states, and there are various types of states. I'll get to that in a second. And the lines that connect states are called transitions. Now, you will see that each of the transitions is labeled, and here just with a 1 or 0. And also, they have a direction. I will just refer to this machine as M1, our machine M1. We'll give it a name. It's not a very fancy name, but it would do. And as I briefly mentioned before, we have different types of states in this diagram. So you will see states with an incoming arrow, actually just one state that only has an incoming arrow, which is the start state. And we would also see final states or accept states. They're represented using the double circle. Now, how do we perform computation using these machines? So the input is just a string of zeros and ones in this case. We would call 0 and 1 the alphabet that we work with. And the output of this process will just be really a binary decision. We're either going to accept the string or reject it. So let's see, we start the process in the start state, and in this case, this is S0. And we follow the corresponding transitions. So we move from one state to another, just using the labels on the arrows. And now at the end, we just check and see what state we're in. If we're in a final state, so the double circle, we will accept the string. And if we're not, we simply reject it. A small note is to just say that we only check the state we're in when we finish reading the string. So it doesn't matter if we go through accept states or not. All we care about it is at the end of reading the input string, are we in a final state or not? So let's just trace an example input through the machine. It's always good to think about examples. And we'll focus on 1, 0, 1, 1. So we're starting the start state, okay, we're in S0, and we read a 1. Where do we go? Well, we go to S0. We then read a 0, therefore moving to S1. We read a 1, that moves us back to S0. And then we read another 1, meaning we would end in S0. The string will be therefore rejected because we ended the computation in state S0. And as you can see, that's not an accept state. It doesn't have the double circle. Another example, 11001. Again, we start in S0, we read the 1 and we stay there. We read another 1, again, remaining in S0. We read a 0, therefore moving to S1. We read another 0, and we move to S2. And then we read the last 1, and we stay in S2. So this string will be accepted because we end the computation in state S2, and this is an accept state on the diagram. So we can represent finite state machines in two ways, either through a state diagram, which is what we've been looking at, or simply a transition table. They really encode the same type of information. It's just two different ways of writing the same thing out. So in a transition table, you would have all possible states as rows in your table. So you see there a row for S0, S1, and S2. And you would have all your inputs, your possible inputs in terms of letters of the string, right? Characters. Here they are digits because we're talking about zeros and ones. They would be there as columns. So you see 0 and 1 as possible inputs. Now, the table tells us what the next state is, depending on the current state, which is represented in blue, and the current input, which is represented in pink. Again, just an example, let's say we're in state S1 and we read a 1, we would go to S0. All right, so one question we might ask about these machines is what language do they accept? So that is, what is the set of strings that is accepted by this machine? Or can we characterize exactly the strings that M1 accepts? It's a very interesting problem. So let's try to figure that out. And I have listed on the right-hand side the strings we've already looked at. So we've figured that the first one is rejected and the second one is accepted. So let's look at a third example. If we trace 0, 1, 0 through the machine, I encourage you to do that. So we start in S0, read a 0, move to S1. We then trace 1, we move back to S0, and then another 0 going to S1. And this will be rejected because S1 is the state we end in, and that's not a final state. In another example, 0, 0, 1, 1, this would end the computation in S2, and this will be accepted because we end in an accept state or final state. We now have a bunch of examples of accepted and rejected strings, but of course we could continue this process forever. And we really need to think about what is represented by this machine. So how and when do we actually end up in an accept state? Here, that being S2. So, of course, we want to start the computation always in S0. That's the start state. And looking at this diagram, when do we actually end up in S2? Well, we end up in S2 if we read 2 consecutive zeros at any point in the string. After we've read 2 consecutive zeros, the string could carry on, but you notice there's a loop around S2, meaning we just stay there. So nothing we read after reading 2 consecutive zeros will impact the decision because the string will be accepted. So M1 accepts exactly those strings that contain 0, 0 as a substring. And just a bit of terminology here. assuming L1 is the set of strings that contain 0, 0 as a substring, as I note on the slide, we might say M1 accepts L1, or M1 recognizes L1, or L1 is the language of machine 1. And a note is just that languages are just sets of finite strings. So throughout your degree in computer science, you're going to have to familiarize yourself with quite formal and potentially heavy notation. So this slide here is not meant to scare you, but really just meant to show you how nice we can lay out information using formal notation. And really, we're just going to read it together, and you're going to see that it all makes sense. So the formal definition, the mathematical definition of a finite state machine is a 5-tuple. And you might wonder what that is. It's just, we need to specify 5 things in order to define this machine. So Q is a set of states. So what are the set of states of this machine? Well, S0, S1, and S2. There are 3 states in this machine. So that would be our set Q. Great. Next is sigma, which we call the input alphabet. So really, what sort of characters, letters, digits do we expect to read in our input string? And in our case, we only worked with zeros and ones. So sigma is just the set that contains 0 and 1. Next, we need to describe the start state, which I listed S in general, but here S, the start state, is represented by S0. 2 more things to go, one being the set of final states or accept states. We've established that those two mean the same thing. And in this diagram, S2 is the only accept state. That's the only double circle that we have in the machine. And we also have the transition function, delta, which you can think of as just the next state function. So I have the formal definition there is a function that takes as input a state, the current state, and the input, the current character we're looking at. And the output of that function is the next state. So we would say, based on the diagram here, that delta of S0 and 0, namely, if I'm in state S0 and I read a 0, where do I go? The output of that is S1. And that is it. That's how we can just describe these machines. Okay, so let's look at another machine now and figure out what is the language of this machine in the same way we did with machine 1. So we'll start as before by tracing through a few example inputs. It's always good to think about some examples before we figure out the general rule. And let's look at 1, 0, 0, 1. We're going to start in S0. We're going to read a 1 and we're going to stay in S0. We then read a 0 and move to S1. We read another 0 and move to S2. And then read the final 1, and we end the computation in state S2, and therefore the string will be rejected. Great. How about another string, 1, 0, 1? We start the computation in S0, we read a 1, we stay in S0, we read a 0, we move to S1, we read a 1, and we finish the computation in S1. Which is an accept state, meaning that this string is accepted by the machine. All right. How about 0, 0, 0, 1? I'm just going to let you trace the string through the machine. Remember, we start in S0. So we read a 0, followed by another 0, by a third 0, and then a 1, and we end the computation in S1. Which means this string will be accepted. And lastly, 0, 0, 1. We start in S0, we read 0, 0, 1, and we end in state S2, meaning the string is not accepted or, well, rejected. Okay, so what is the language of M2? We notice that reading once doesn't really affect the next state. As in, you notice the loops around all of the states. So when reading one, we simply just stay in the same state. But when we read zeros, we tend to move between the states. So we only move between the states when we read zeros. So it must, this machine must compute, do something with the zeros or care about the zeros. And the way to end up in S1 really is to read an odd number of zeros. So if we read 1, 0, we get to S1. Then if we read another 0, so 2, we're going out of S1. And then the only thing that brings us back is if we read a third 0, and this process carries on. So M2 really accepts exactly those strings that contain an odd number of zeros. Great. Our next task, now that we have machine 2 and we figured out what it does and what the language is to think about simplifying this machine. Or rather, is this the simplest machine we can build that has this language? Or can we simplify it in some way? And what does that actually mean? How do you simplify these machines? Well, we can't really reduce the number of input symbols. We need to think about zeros and ones, but we might try to reduce the number of states. So can we build a machine with less states than 3? I mentioned previously that these machines have a very limited amount of memory, but they don't have a memory in the traditional sense of storing arbitrary data, but their memory is really restricted to just the state that they're currently in. So we really need to think about what we need to keep track of and make a state for each of these things that we want to keep track of. Remember that M2 accepts all strings with an odd number of zeros. So representing the number of zeros we've seen so far is probably a good idea. And are there any two states in this machine M2 that are equivalent? So let's see. We start in S0, and at this point, we've not seen any zeros. When we're in S1, we have read 1, 0. And when we're in S2, we have read 2 zeros. What happens if we read a third 0? Well, we go back to S1. And what happens when we read a fourth 0? We go back to S2. So now we're in S1 if we read 1 or 3 or 5 zeros. And we're in S2 if we read 2 or 4 or 6. So an even number of zeros. And we note that S1 is an accept state, which we probably really need to keep. So what about S0? Is there really any difference between S0 and S2 in terms of what we're trying to represent? Well, not really. In S0, we have an even number of zeros, but just we've not read any yet. So 0 is an even number. And S2, we've established we're going to end up there if we've read 2 or 4 or 6 number of zeros. So really, this would be the equivalent machine, and we'll call it M3, which is in fact the simplest machine we can build for the task. So we only need 2 states. I've called the first state even, and that's going to be our start state. And the second state is called odd, because that's really what we're representing in this machine. And we move between them according to, or rather when we read any zeros. All right, I did warn you about doing just a bit of work. So it is time for you to build your very first machine. You might want to take a piece of paper and try to draw a finite state machine that recognizes the strings we have on the slide, which are 0, 0, 0, 0, 0, 0, and so forth. I will just patiently wait for 1 minute and you can just make a start. All right. You might not have finished building the machine, but I hope you at least made a start, and we'll walk through this together. So the first reasonable thing to do is probably to start with the start state. And we definitely need that. Let's call it a 0. And if we read a 0, we know for a fact that this should be accepted, right? That fulfills the first condition. Great, so we have two states, S0 and S1, out of which S1 is an accept state. Okay, so now if we read another 0, we should stay in the same state. Or rather, we could move to a different accept state, but we really want to use a finite amount of states, and it's a very good idea to just stay in the same state. Any further zeros that we read should obviously do the same thing. This is correct according to the condition. The string will still be accepted. But what happens if we read a 1 at the beginning? So we've discussed a case where the string starts with a 0. What about the case where the string starts with a 1? Well, we can't go to S1 because that's an accept state. So we need to draw a third state. We'll call it S2. And really anything we read from that point onwards is not going to change the outcome. We will need to get stuck there in S2 because we can't accept the string anymore. But what if we read a 1 when we're in state S1? We should also reject. And again, anything else we read from this point, we'll also not change our decision. So it's sensible to move to state S2, where, as we just said, we're going to stay forever until the string ends. And notice that this state S2 really just represents the reject state. We can't move out of it since once we read a 1 in the input string, that means it's invalid and it shouldn't be accepted. So we're in a lucky situation in which we can actually decide whether the string is accepted or not. In some cases, rather when the string is rejected, we can decide earlier than when the string ends. So one last puzzle for today. We have these two machines, M3, which was just a machine that contained, or rather accepted, strings that contain an odd number of zeros. And we had machine M4, which we have just built together, where that only accepts strings that contain only zeros. Great. We would quite like to build a machine, M5, that accepts the same strings as M3 and M4, but no others. Now, formally, with the notation we had before, the language of machine 5, which is this machine we're trying to build, should be just the union of the languages of machine 3 and machine 4. And this should just be union of two sets. Okay. So how might we do that? Well, the trick would be to simulate running these two machines in parallel. We might want to start both of them in their respective states. So that would be, I want to start machine 3 in the even state and machine 4 in S0. Okay, so now every time I read an input symbol, I want to move in both machines accordingly. So if I read a 0, machine 3 will move to the odd state, and machine 4 will move to S1. When we finish reading the input string, what should we do? Well, according to the rules, we need to check whether we're in a final state in either machines. Okay. But what are the states of this finite state machine that we're trying to build? Ordered pairs might be a good idea. We've noted here on the slide the ordered pair XY, where X represents just a state in machine 3 and Y a state in machine 4. This is a very sensible way to capture the respective states in the two machines we care about. So let's see. Machine 3 has the states even and odd, and machine 4 has the states S0, S1, and S2. So therefore, machine 5 should have 6 states. Even and S0, even and S1, even S2, odd S0, odd S1, and odd S2. So all possible combinations that we can get by putting together states from machine 3 and machine 4. Right, so we established what the states would be and how the new machine will transition to the next state. Really, it's just going to follow whatever the initial machines are doing. So it can just use their transition functions to move. But what are the accept states of this machine? So, okay, the task is to accept the string if either machine 3 or machine 4 accepts it. So if either machine 3 or machine 4 ends in an accept state. I've noted the final states in red. Again, the odd state and state 1 are the accept states in M3 and M4. So what should be the final states in M5? Well, it should be all the pairs that contain at least one accept state. So if in the ordered pair, we see the odd state, that should be accepting regardless of what odd is paired with. Or if we see S1 in the pair, again, we should accept that regardless of what that state is being paired with. And here is the final machine. Now, let's walk through some examples. This machine will accept strings that have an odd number of zeros or only consist of zeros. All right, so let's think about 0, 0, 1. Okay, so that means we start in even S0. We read a 0, we move to odd S1. We read another 0, we move to even S1. And then we read a 1 and we move to even S2. And that's where the computation ends and we reject the string. Is that a sensible thing to do? Of course, the string 0, 0, 1 doesn't have an odd number of zeros and also does not contain of only zeros. So neither machines is going to accept it. How about the string 0, 0? Well, we start in even S0. We move to odd S1, and then to even S1, which is an accept state. And this would mean that the machine, this resulting machine 5 will accept it. Is this correct? Yes. That's because 0, 0 is a string that machine 4 accepts because it only contains zeros. How about the string 0, 0, 0? Okay, so if we trace the computation again, we start 0, 0, 0. We end in the state odd S1, which we notice again is accepting. Is this reasonable? Absolutely. The string 0, 0, 0 is accepted by actually both machines. because it has an odd number of zeros and also only consists of zeros. And there we are. So let's see what we've learned in today's lecture. We looked at the definition of a finite state machine. We've seen how we can use finite state machines for computation, and we have looked at how we can identify the languages accepted by various finite state machines. We have looked at constructing our own machines with different specifications, and I hope that was a fun puzzle for you to solve. There's many more from that you can try alone. And we have also looked at combining these machines through the union operation. So we built a machine that accepts the language, the union of the two initial languages. This is the end of the lecture. I want to thank you for your attention. I hope it was captivating and it gave you just a flavor of really what you will learn in a computer science degree, particularly in Cambridge, but anywhere else really. This is one of the foundational concepts we see in discrete mathematics, which is maths for computer scientists. I will try to maybe look at some questions. I see Emma. Hello, welcome back.
Yes, thank you so much. Yes, there's an interesting question here. I'm happy to about what level of difficulty this lecture is in sort of comparison to the content taught at Cambridge.
Yeah, so this would be something you would talk about in really your first year. As I said, it's part of what we call discrete maths, which is maths for computer science. So it would be one of the initial lectures in that topic, but it would happen a bit further on in your second term at Cambridge.
Great. And then we've just got here, how extensive is machine learning or artificial intelligence at Cambridge?
Yeah, well, we're reproducing whatever's happening in the world, right? So machine learning has really taken off. The research is there's a lot of groups that have delved into doing research in machine learning. So there's a lot of it. Now, of course, there's still, as I said, some really important things that you need to learn to really even start understanding how to build your own algorithms for machine learning rather than just using some off the shelf. So you will do machine learning in your first year, which is quite an exciting course where you get to play around with very, simple models at first. So you do that from your first year on to your third year, when you can choose your specialist courses on machine learning. You can do a machine learning final year project and dissertation. And why not stay on if you want for a master's or a PhD. So yes, it's quite extensive. And nowadays, really, machine learning is at the intersection of any two areas. So people have really expanded.
Great, thank you. And another good question here is about sort of books, articles, podcasts you could recommend for those looking for greater understanding in computer science.
Right. So there's a lot of things you can do, and actually, I might have a slide about that. Not about the books in particular. What I can do is I would be able to send out maybe through Emma if
yeah, absolutely. Yeah. I can send
Okay.
anything on to everyone who's attended
so
today.
If you email Emma at outreach@Murray-Edwards, I'll make sure we reply with just some suggestions. So really, we tend to recommend kind of books on operating systems and thinking about those. Any sort of programming really you can do is great. Computer science is not it's not only about programming, but programming is a good way to learn some of the required skills. Other things you can do, I know you asked about the books, but it's really about experience. So participate in UKMT senior maths challenges, participate in any capture the flag competitions, national ciphers challenges. Of course, some what we call passive learning, watching online lectures, reading books, that's really great. But also just hands-on experience with, for example, hardware, get the Raspberry Pi and play around with it. So it's really about thinking of all those things that would set you put you in a very good position for the upcoming admissions.
Thank you so much. Maybe we'll just have a couple more questions. Luana, have you managed to access them, or shall I keep on choosing?
No, please. Yeah. Please.
Let me have a look.
I also like the interaction with you, which is great.
Okay, this one is more sort of subject specific in terms of your lecture you've just delivered, and it is: would finite state machines come under set theory? And if not, what area of maths does it come under?
Well, you've seen that we use set theory. So set theory is a prerequisite for this. It's in part of math that we talk about finite state machines, finite automata, and regular languages. So the big computational theory area that I talked about. So I think that would be the answer. But it's something you would do under the big umbrella of discrete mathematics, which works with sets, which is why we call it discrete rather than continuous. So
Fantastic.
it uses set theory, yes.
And then we've got more of a question about you here, which I'm also interested in. What aspect of computer science interests you the most?
Right. Well, it's quite natural that it would be the research I'm doing, which is at the intersection of linguistics and computer science. And I am a computer scientist, so my degree is in computer science, my postgrad degrees are as well. But I found it really, as I said, interesting to see where we can use where I can use my computer science knowledge and the intersection of computational or linguistics and well, computer science is what I chose. So to me, obviously, this falls under the big umbrella of machine learning, but really also about you know, how should we really represent the meaning of words? Humans are really good at talking, understanding really natural language. And computers were up to, well, very recently quite bad at it. So this field has now completely, you know, blown out of proportion with ChatGPT and whatnot. But it's really about that. So how can we, you know, really represent meaning of words in computers? Is text enough? Probably not. As humans, we learn from not only from text, from reading books, from, you know, listening to others and talking to other people, but also through our eyes. We look at images, we, you know, see our surroundings, also through other senses like smell or touch. Should we incorporate all of those in order to really have a model that understands what words mean? Or is it enough to just give the model, you know, a huge chunk of text describing cats? Will it learn really what cats are? That sort of thing.
Great, fantastic. Well, there's loads of questions, and we're getting more and more through, but I think we are just about running out of time. Luana, I wanted to say on behalf of everyone, thank you so much. And just to reiterate, this will be added to our YouTube channel in the coming weeks. And please do drop outreach at murrayedwards.cam.ac.uk and email with any questions, and we will either perhaps check in with Luana, or we'll do our best to answer them too. Fantastic. Okay, well, thank you so much, Luana, and thank you so much, everyone. Thank you, Luana, and I think we'll sign off.